Hello, this is Tanfer. I'm a doctoral researcher at Karlsruhe Institute of Technology in Germany. I will present SlackHammer, logic synthesis for graceful errors under frequency scaling. Traditionally, timing guard bands ensure error resilience at the circuit level, but in advanced technology nodes, process and runtime variations have high margins. Alternative approaches embrace the error. For instance, approximate computing allows the error as long as the output quality is acceptable. The idea behind using timing speculations, meaning invoking timing errors, is that it happens rarely. The most input combinations do not invoke the critical path, so they can be done in a shorter time or at a lower voltage. We put this into experiments and see that it actually does not hold. In this example, we synthesize a 64-bit adder with a delay constraint of 0 nanoseconds. In y-axis, we share the delay, and in x-axis, we enumerate the primary outputs. We observe that most primary outputs have a delay between 0.22 and 0.28 nanoseconds. It's centralized rather evenly around 0.26. When we synthesize this adder with a delay constraint of 0.26 nanoseconds, we observe a more even delay distribution. Further, when we synthesize a 32-bit adder, which could be faster, but with the same delay constraint, 0.26 nanosecond, again, we observe this even delay distribution between the primary outputs. Here, we would pick a safe clock period with timing guard bands, but with fluctuation in voltage or frequency, most primary outputs become error-prone. This is because traditional synthesis algorithms apply delay optimizations only to the most critical path at each iteration. Afterwards, they apply area optimizations to the short paths. Traditional synthesis algorithms aim at balancing the delay of each and every path. Under frequency or voltage fluctuation, invoking any of these paths lead to an error. In contrast, SlackHammer optimizes all paths, including the non-critical paths, and with voltage and frequency fluctuations, the probability of error is reduced. We do that by setting delay constraint to each primary output. Here we compare a 16-bit multiplier synthesized with the traditional algorithm with a delay constraint of 0 nanoseconds against SlackHammer. We compare error rate and the magnitude as we increase the frequency beyond the design frequency. Note that y-axis is logarithmic, and both of these circuits start producing error exactly at the same frequency. As we increase the frequency beyond the design frequency, we observe that SlackHammer circuit has up to 15x lesser error rate and up to 7x less error magnitude. Precision scaling is a very popular method in approximate computing. Following the previous example, if we use only the 8 least significant bits, the circuit produced with the traditional synthesis algorithms produce errors starting at 1.1 times the design frequency. In comparison, SlackHammer circuit starts producing error at 1.23 times. Thank you for watching the video. This was SlackHammer logic synthesis for graceful errors under frequency scaling. You can find more information in the IEEE TCAD paper.